The topic of this video is about dimensional analysis. So what is dimension? Dimension of a physical quantity express its dependency on the base quantity at a products of symbol or of their power representing the base quantity. So what are the base quantity? They are length, which we use the symbol L, mass, use the symbol M, and time, we use symbol capital T. Okay. So for example, the area have the dimension of L square. The speed, what you're probably familiar with, is like mile per hour. That's the distance, length per time. So that will be LT to the minus 1 power. If you have a quantity that when you write the power, all of the power are 0, then you call that a dimensionless quantity. And you can write it to be a number of 1. So basically, if you have a number, that is a dimensionless quantity. When writing, we use the square bracket around the symbol to represent the dimension. So for example, bracket R, which means the dimension of R, or radius, is L. This is bracket A, the dimension of area is L squared, and so on and so forth. A physics equation must be dimensionally consistent. So what does that mean? It means the equation must obey the following rule. 1, every term in the expression must have the same dimension. You cannot add apple and orange, right? And expression on either side of the equality in the equation must have the same dimensions. You cannot equate apple and orange. Okay. Third, the argument of any of the standard mathematical functions, such as trigonometric function, like sine, cosine, tangent, or logarithmic or exponential function, must be dimensionless. So let's check some of the equations to see whether they are dimensionally consistent or not. Okay, so here's an example that we can go through. We are given the dimensions of S, for example, distance, to be L, little v, like speed, or v stands for velocity, is L t to the minus 1. A for acceleration, which is the rate of change in velocity, is L t to the minus 2 power. And lastly, time dimension is capital T. Okay. So we would do this example, and later on what you would find is that knowing how to check a dimension, you would it would help you to remember equations better, and it's also help you to check your work. So let's go to the whiteboard so we can do that problem. So I already copied the problem here. Okay. So these are the thing. These are the base. These are the dimension that given. So let's highlight that. Okay. And let's do the first one. So I'm just gonna copy down the equation. S is equal to Vt plus 0.5 a t to the square. So when we check dimensional consistency, basically we put bracket around it. So dimension of Vt, each of the term, 0.5 a t to the square. So let's check each term. So dimension of v dimension of vt is the products of dimension of v and dimension of t. And dimension of v is L t to the minus 1 power multiplied by another t. So that's just L. The dimension of 0.5 a t to the square is the same as the dimension of 0.5 is just 1. So let me actually write it down. Multiply by dimension of a and dimension of t to the square. So that's just 1. And then dimension of a is ln t to the minus 2. And then t to the square. So that's essentially just L. So now what we see here is this. Give it L. This gives us another L. And this gives us another L. So right away we see that the first condition satisfied. Both of this are the same. The two terms that we add have the same dimension. And this is also equal to L. So the two terms on both sides of the equation have the same dimension. So this is dimensionally consistent. Okay, so let's do the second one. So I'm just going to write it down as is equal to vt to the square plus 0.5 at. So let's checking its dimensions, which is vs is equal to dimension of vt square plus dimension of 0.5 at. Okay, so let's do dimension of vt square. That's dimension of v multiplied by dimension of t to the square. That's ln t to the minus 1 multiplied by t to the square. And that is LT. The dimensions of 0.5 AT is dimension of 0.5 multiplied by dimension of A multiplied by dimension of T. So that's 1 ln 2, let's see, to the minus 2 multiplied by t. So that's L t to the minus 1. So let's see here. So let's go back and what we see here. This is give us an L. This one give us a LT. And this one give us an LT minus 1. So as you can see, this term right here and this term right here, they do not have the same dimensions. So you cannot add apple and orange. So therefore, they are not dimensionally consistent. Okay. Let's do C. So V equals psi A t to the square divided by S. Okay. So what we want to check is whether dimension of V is it the same as dimension of this psi A t square over S. Okay, dimension of A t to the square over S. Well, we did have a t square over here before, and that's an L. And dimension of S is also an L. So that's the 1. So that's good. We have this thing to be 1, which is a dimensionless. So that's a good check. Right? And the psi of an angle or a radian is also a 1. So over on the left-hand side here, we have this quantity to give us 1. But on the left-hand side is dimension of V is length t to the minus 1. So obviously, they are not equal. So this equation is also not dimensionally consistent. Okay. Let's go back here a little bit. As you can see, if we focus between this equation and this equation, the difference here is this power switch between that term and that term. Okay. So now you can see that knowing how to check the dimension of an equation allow you to remember which one is the correct equation to use. Okay. And imagine you have gone through a lot of math and derive an equation that looks something like this. And as you can see that that's not dimensionally correct, therefore the equation is not correct. So you must have made a mistake along the way somewhere. So you should go back and check your work. So dimensional analysis is very important for your understanding of the equations and checking your work to see whether your work is correct or not.